Welcome to our presentation on basic single equation analysis. We will bridge the gap between econometric theory and practical application using EViews. The core idea is that economic theory provides the framework for our models. EViews is the powerful tool we use to estimate these models and analyze data. And ultimately, our job as economists is to interpret these results and tell a meaningful story. This session will cover the entire workflow, from ordinary least squares to advanced diagnostics and forecasting using EViews 13 and 14. Imagine you have a theory that education impacts wages. Theory gives you the model wages equals F of education. EViews helps you find the specific numbers, like a 10% wage increase per year of education. You then tell the story of how education is a worthwhile investment. So why do we need to go beyond simple intuition and quantify these relationships in the first place? Let's explore that next. We often begin with a general intuition, for example, that more education probably leads to higher wages. But simply thinking variables are related isn't enough for robust analysis or informed decision-making. The real power comes from quantification. Our goal is to move from this intuition to precise measurement. Instead of just asserting education helps, we aim to estimate specific parameters, such as one additional year of education increases wages by 8%. This precision also allows us to understand and minimize the inherent uncertainty in these relationships. The key solution here is regression analysis. This powerful statistical technique allows us to isolate the specific impact of one variable, like education, on another, such as wages, while holding all other relevant factors constant, a concept known as ceteris paribus. Choosing the right econometric model is a critical first step in any analysis. Our flowchart provides a roadmap, starting with the nature of your dependent variable. If it's continuous, like income or sales, you'll typically begin with ordinary least squares, or OLS. If it's discrete or limited, such as a binary yes-no outcome, models like logit or probit are more appropriate. Regardless of your initial choice, thorough diagnostics are essential. You must check for issues like serial correlation, particularly with time series data, which may require adding AR or MA terms to your model. Equally important is checking for endogeneity, where an explanatory variable is correlated with the error term. This often necessitates the use of instrumental variables, such as TSLS or GMM. Beyond these, always consider your data's frequency, whether it's time series or cross-sectional, and rigorously examine the error structure of your model. Issues like heteroscedasticity, for instance, often call for robust standard errors to ensure valid inferences. The foundation of single equation analysis is the linear regression model. In its simplest form, with one independent variable, we represent it as yt equals beta 1 plus beta 2 xt plus epsilon t. Here, yt is our dependent variable. Xt is the independent variable, beta 1 is the intercept, representing the value of y when x is 0. Beta 2 is the slope, indicating the change in y for a 1-unit change in x, and epsilon t is the error term, capturing all unobserved factors. The core objective of ordinary least squares, or OLS, is to identify the values for beta 1 and beta 2 that minimize the sum of squared residuals. These residuals are simply the vertical distances between each actual data point and the estimated regression line. Conceptually, OLS seeks the line of best fit that results in the smallest possible total error between our model's predictions and the observed data. In practice, software like EViews uses matrix algebra to efficiently calculate these coefficients, utilizing the formula for the beta estimator as the inverse of x prime x multiplied by x prime y. This mathematical approach guarantees a unique set of coefficients that achieve our minimization objective. However, for these OLS estimates to be truly reliable and possess desirable statistical properties, a set of underlying assumptions must be met. Let's delve into those crucial conditions next. The classical linear regression model, or CLRM, relies on several key assumptions for ordinary least squares to provide reliable estimates. These include linearity, meaning the model is linear in its parameters, exogeneity, where the error term is uncorrelated with our independent variables, homoscedasticity, implying a constant variance for the error term across all observations, and no serial correlation, which means errors are random and not correlated with their past values. However, these ideal conditions are often violated in real-world data, requiring specific remedies. If we encounter heteroscedasticity, where error variance is not constant, our standard errors become incorrect. The solution is to use white or HAC robust standard errors. When errors are correlated over time, known as serial correlation, we can address this by incorporating ARMA terms into the model or employing Newey West standard errors. Most critically, if an independent variable is correlated with the error term, leading to endogeneity, a violation of exogeneity, our coefficient estimates will be biased. In such cases, instrumental variable methods like two-stage least squares or generalized method of moments are essential for valid inference. We've covered the theoretical underpinnings. Now let's explore how to actually perform estimation in EViews. You have two main pathways. The most direct method is using the command line. For instance, typing LSYCX immediately runs a least squares regression, where y is your dependent variable, c represents the constant, and x is your independent variable. The ls command itself is shorthand for least squares, providing instant results. Alternatively, you can use the graphical interface by navigating through the menus. Select Quick, then Estimate Equation. This brings up a dialog box where you can specify your equation, estimation method, and sample range. Once your regression is run, you'll want to perform diagnostics. For that, you would go to View and then select Residual Diagnostics. When using the graphical user interface in EViews, you'll primarily interact with the equation estimation dialog box. It's here that you specify your econometric model. First, in the Equation Specification field, you enter your dependent variable, followed by c for the constant, and then your independent variables. For example, log of CS, c, log of inc, as shown here. Next, under Method, least squares, or LS, is the default and often your starting point for estimation. You then define your sample period, which can be a simple date range like 1990-2020, or include conditional statements to select specific data points. Finally, for advanced options, such as correcting for heteroscedasticity or serial correlation using robust covariance methods like HAC or white, you would navigate to the Options tab. This dialog provides a comprehensive interface for setting up your regressions. For our practical case study, we'll dive into the NYSE volume dataset, which holds extensive historical trading data from the New York Stock Exchange. Our main objective is to analyze the underlying trend in the logarithm of trading volume over time. We apply the logarithmic transformation to volume to help stabilize its variance and allow for easier interpretation of changes in percentage terms. A critical first step in any robust econometric analysis is to thoroughly inspect your data. Wayverify bet our sample range covers a substantial period, from the first quarter of 1888 right up to the first quarter of 2004. Furthermore, it's always essential to check for any missing values, often denoted as NA, as these can significantly impact our estimation results if not properly addressed. In EViews, as shown on the left, we identify log vol as our dependent variable and a time trend, represented by T or @trend, as our key regressor for this analysis. With the data now properly set up and inspected, we are ready to proceed to the next stage, running the regression and interpreting the output. After running your regression, EViews presents a detailed table of results. The first key metric to examine is the p-value, often listed under prob for each coefficient. A p-value less than 0.05 allows us to reject the null hypothesis that the coefficient is 0, indicating that the variable is statistically significant. For example, in our output, the trend variables and the ARMA terms all show very low p-values, confirming their significance. Next, we look at the R-squared value. This statistic tells us the proportion of the variance in our dependent variable that is explained by our model's independent variables. A value closer to 1.0, like the 0.9875 displayed here, indicates an excellent model fit, suggesting that nearly 99% of the variation in log vol is accounted for. Finally, for time series data, the Durbin-Watson statistic is crucial for detecting first-order serial correlation in the residuals. Values less than 1.5 typically suggest the presence of positive serial correlation. In this case, our Durbin-Watson statistic is 1.986655, which is very close to 2, indicating that we do not have a significant issue with positive first-order serial correlation. The Durbin-Watson test is a good starting point, but a more detailed way to diagnose serial correlation is by examining the correlaogram of the residuals. To effectively diagnose whether our model suffers from serial correlation, we utilize a crucial tool, the correlogram. This chart visualizes the autocorrelation, or AC, and partial autocorrelation, or PAC, of the model's residuals across various lags. A significant spike in the AC function, extending beyond the dotted significance bounds, strongly indicates that our residuals are correlated with their past values. Simultaneously, the Q statistic and its associated p-value provide a formal joint test for serial correlation. If these p-values are small, typically less than 0.05, we formally reject the null hypothesis of no serial correlation. When we observe these significant spikes, it's a clear signal that the error terms are not random. This directly violates a core assumption of the classical linear regression model, implying that our current model is likely misspecified and its inferences are invalid. In EViews, you can access this diagnostic by navigating to View, then Residual Diagnostics, and finally Correlogram. To effectively address the serial correlation we diagnosed, we augment our regression model with ARMA terms. The EViews command is updated to include AR1, AR2, and MA1 alongside our constant and time trend, as shown. The AR terms, such as AR1, correct for the correlation with the dependent variable's past values, specifically at lags 1 and 2. The MA1 term, on the other hand, accounts for the correlation with previous periods' error shocks. As we can see from the regression output, these newly introduced ARMA terms are highly statistically significant, with p-values far below 0.05. A critical check for time series models is stability. This is confirmed by ensuring that the inverted roots of the AR and MA polynomials lie within the unit circle, meaning their values are less than 1. Here, our inverted AR roots are 0.96 and 0.34, and the MA root is 0.73. All are indeed less than 1, confirming our model is stable. Furthermore, the Durbin-Watson statistic has improved to 1.986655, indicating that we have successfully mitigated the serial correlation issue. When you have a large number of potential explanatory variables, automated selection methods become incredibly useful for constructing a parsimonious model. One prominent approach is the general to specific, or GETS, methodology. These algorithms aim to optimize the model either by maximizing a measure of fit, such as the adjusted R-squared, or by minimizing information criteria, like the Akaike, AIC, Schwartz, SIC, or Hannon-Quinn, HQ criteria. These criteria are designed to strike a balance between a model's explanatory power and its complexity, penalizing the inclusion of too many variables. Various techniques fall under this umbrella, including unidirectional, combinatorial, and auto-search methods like stepwise regression. However, it's crucial to heed this warning. Automated variable selection is a statistical tool to aid your analysis, not a replacement for sound economic theory. Relying solely on these methods without theoretical justification for the chosen variables can lead to spurious results in data mining. Always ensure your selected variables are theoretically grounded. This process helps us choose the right X's for our models. But what if one of those X's has a more fundamental issue, such as endogeneity? This slide focuses on addressing endogeneity, a significant challenge where an explanatory variable is correlated with the error term, leading to biased and inconsistent OLS estimates. The primary solution involves using instrumental variables. A valid instrument is one that is correlated with the endogenous variable, but remains uncorrelated with the error term. Methods like generalized method of moments, or GMM, and two-stage least squares, or TSLS, are employed in this context. The EViews interface on the left illustrates how to set up a GMM estimation. Here, you define your main equation, for example, inf c_inf minus 1 unrate minus 1, and then provide a separate list of instrumental variables, such as c unrate minus 1, inf minus 1, inf minus 2. After estimating, it's crucial to test the validity of your instruments. The J statistic is used for this purpose, specifically testing the over-identifying restrictions. A high p-value for the J statistic indicates that we cannot reject the null hypothesis that the instruments are valid, providing confidence in our model's estimates. Once we have estimated a robust model, its primary application often lies in forecasting future values. EViews provides two distinct approaches to forecasting. First, a dynamic forecast uses previously forecasted values as inputs to generate subsequent predictions. This method is particularly useful for multi-step ahead forecasting, allowing us to project the long-term trajectory of a variable. For instance, if forecasting quarterly GDP, a dynamic forecast would use the predicted Q2 to then predict Q3, and so on. Conversely, a static forecast always relies on the actual historical values to produce a one-step ahead prediction. This approach is generally more accurate for evaluating the models in sample fit. To assess the quality of these forecasts, we examine key metrics like the root mean squared error, or RMSE, and the Thiel inequality coefficient. Lower values for these indicators suggest higher forecast accuracy, indicating our model's predictions are closer to actual outcomes. This concludes our discussion on the single equation analysis workflow. Let's now summarize the key takeaways. As we conclude, let's recap the final takeaways from our session. First, remember that single equation analysis is the fundamental building block for all empirical work in econometrics. It's the essential starting point for understanding complex relationships. Second, always prioritize mastering your diagnostic tests. These are crucial for ensuring the validity and reliability of your model's estimates, moving beyond just checking the R-squared. As we've emphasized throughout, theory guides the model. EViews crunches the numbers, but ultimately,